Okay, here's the next problem. So the switch here is open. Okay, the switch here is open. What I need to find is the potential difference across the switch. Okay, very good. So one can in principle simplify this circuit. No, I don't want to simplify anything, so I will just treat this circuit as it is, and I will solve it using Kirchhoff's rules. So I will start from giving names to all the currents. So this will be I1. It's the current through the through the battery I1. So this will be I2, and this will be I3. So I actually can say something about the current I3 right away. Since the switch is open, the current has nowhere to actually flow. So I3 is just 0. Okay, and therefore the rule, the current rule for that node is easy to find to write. So I1 is the only incoming current. So what our outgoing currents is I2 plus I3, but I3 is 0. So therefore it is just I2. Oh, well, sorry. I2, in other words, it means that I1 equals I2. Very good. So the next thing, I'm going to go around all these, all whatever I see in the circuit and place the direction of the potential difference. So for the battery, I use from the low to high. For loads, I use the rule that it has to go opposite to the direction of the current that here and here. Very good. So, and for deltas v switch, I need to define the direction. Well, I will define direction in this way, but I might potentially get a negative result, and therefore I will have to rethink where my low and high voltages are. So we will see. So right now, the way I assign this delta V switch might potentially become negative, but we will see what we'll get at the end. So the next step is to define the loops. Well, let's consider the loop, this large loop over here. I'll call it A. We can introduce other loops as well. We can introduce the loop B, but let's just do that. So for the loop A, I might also define the loop B, but we'll see. Maybe this is sufficient already. For the loop A, I will write the loop rule. So it's 4 volts with positive sign minus. Now I go through that load. The direction of the potential difference across this load is opposite to the direction how I go around this loop. So it's minus I1 times 2 ohms. 2 ohms. Okay, next, what do I encounter here? Okay, delta V switch, and it will be with minus sign switch. Why? Because the direction of how I go around this loop is opposite to the direction of the potential difference. The way I define that. The next contribution is due to this battery. So I go around this loop. This one is coincide, so therefore it will be positive sign. So plus 2 volts, and I ended up at the same place, and therefore it's 0. 0. Very good. Can I simplify this a little bit? I can. I see from here that I can join these two here together, so I'll get 6 volts minus I1 times 2 ohms minus delta V switch equals 0. Very good. So now let me actually consider the loop. Which loop would be easier to consider, but which would involve actually the current. Yeah, doesn't really matter. So let's consider that loop. We'll consider this loop. Let's call it loop B. Okay, for the loop B, what we're gonna get? Please pause the video and try it yourself. Okay, I get minus 12 volts This is when I go across this battery, right? So the direction how I go around the loop is opposite to the potential difference. So it's minus 12 volts. Then I go further away, so it will be minus delta V switch. Then I go through the battery over here. It gives me positive 2 volts plus 2 volts. Then I go through that load and the direction coincide this time, so it is plus well, let me start with writing the current plus I2 times 2 ohms, and that's 0. What I know about this is that I2 equals to I1. Okay, so therefore I can rewrite this equation. So let me just rewrite right away. So this I will combine together. I will get negative 10 volts minus delta V switch. And here, instead of I2, I will use I1 just because the I2 equals to I1. So plus I1 times 2 ohms, and that's 0. Very good. So now I have two equations. So this one equation, this is another equation, and two unknowns. Okay, so let's express I1 from this equation and substitute it into that equation. As a matter of fact, what I want to actually express is I1 times 2 ohms from this equation, from the equation A. Okay, so let's just do this. So from the equation A, what follows is the following, that I1 times 2 ohms is nothing else but 6 volts minus delta V switch. So how did I get that equation? Well, the only thing I've done, I just took that thing and I transferred it into the right hand side. And when I transferred it, flip the sign, and so what was left on the left, but now it's on the right, is 6 volts minus delta V switch. Okay, so I will just use that, okay, and I will substitute these into equation B over here. I mean, just the combination is the same, and therefore it's easier to do that way. I will just substitute, right? So I will obtain from the equation B then. So again, so what I'm doing, I will use this fact over here. Okay, so what I obtain is that negative 10 volts minus delta V switch, and then I substitute, okay, plus 6 volts minus delta V switch, and 0. Okay, now I can simplify. So I will combine these two together. I will get minus 4 volts, and I combine these two together. I will get minus 2 delta V switch and 0. So now I can solve for delta V switch to get negative 2 volts. And you see that this time it's actually negative. Okay. That means that I didn't choose the right direction. So I want to redraw this potential difference over here. Let me just simplify a little bit. This potential difference over here. So previously it was like that. So I know that I didn't define it, the most appropriate way. So I got a negative sign. So as a matter of fact, it will be like this. The potential difference, the actual potential difference will be like this. With delta V switch, once I switch that direction, will be positive 2 volts. Okay, if the potential difference is like this, it means that this is low voltage terminal and this is high voltage terminal. And that's essentially the answer.